How are quantum gates different from classical logic gates? Have you ever wondered how the building blocks of quantum computing differ from those of traditional computing? Let's break down the differences between quantum gates and classical logic gates. First, let's talk about the basic information units. Classical logic gates work with bits. A bit can only be in one of two states, 0 or 1. In contrast, quantum gates operate on qubits. A qubit can exist in multiple states at once, thanks to a property called superposition. This means a qubit can representing 0, 1, or both at the same time. This ability allows quantum gates to handle more complex information processing. Next, we look at how these gates operate. Classical gates perform deterministic Boolean operations like AND, OR, and NOT. The outputs from these gates are predictable and defined by truth tables. On the other hand, quantum gates perform transformations on qubits using unitary operations represented by matrices. These transformations can create and manipulate superpositions and entanglement. Entanglement is a unique quantum phenomenon where qubits become interconnected. The state of one qubit can instantly influence another, no matter how far apart they are. Another difference is reversibility. Most classical gates are irreversible. For instance, if an AND gate outputs 0, you cannot determine the exact inputs that led to that output. This results in information loss and energy dissipation. Quantum gates, however, are inherently reversible. Their unitary nature allows the original input state to be recovered from the output. This reversibility is essential for quantum algorithms and aligns with the fundamental laws of quantum mechanics. When it comes to circuit construction, classical circuits combine gates in fixed sequences to perform logical operations on bits. Quantum circuits, however, combine quantum gates where the order and interaction of gates are vital. This is especially true because of entanglement and interference effects, which do not have classical counterparts. The computational impact of these gates is also noteworthy. Classical gates process one definite input state at a time. Quantum gates enable quantum parallelism. This means quantum computers can process multiple possibilities simultaneously within a superposition. This capability allows them to potentially solve certain problems faster than classical computers, such as factoring large numbers or searching databases. Lastly, let's look at examples of these gates. Classical gates include AND, OR, and NOT. Quantum gates include the Hadamard gate, which creates superposition, the controlled NOT gate, which entangles qubits, and Pauli gates. In summary, quantum gates differ from classical logic gates primarily because they manipulate qubits capable of superposition and entanglement. They operate through reversible unitary transformations and enable computational processes that can outperform classical methods for specific tasks. These differences form the foundation of emerging quantum computing technologies, which aim to solve complex problems beyond the reach of classical computing.